Now. All right. So thank you all for attending today's presentation, talk, blog post discussion. Not really sure what exactly I want to call it just yet, but for the sake of the brevity that we want to keep for today, let's try and call it an event broadly. So that being said, let me share my screen here. Now, by the end of today, or by the end of this hour, I'd like to ideally have us all be at a point where we can look at this image at the front of the blog post and be relatively comfortable with having at least a rough conceptualization of what is being shown in this document here. So having a rough idea as to what each of these things within the documentation for that blog post shows, like the image kind of outlining the structure of the infrastructure that Meta has open and available for us all to review. So I'm also going to go through and read through the blog post. We're going to bounce around between different visuals and references, different links that might be relevant to the given context that we're covering. So maybe if there's some jargon, I'll take some time to try and explain that, or also provide some information where we all can get a better understanding as to what's going on with the different parts of this infrastructure. Now, with that being said, let's take it away. So this blog post was an effort made to show Meta's major investment into the generative AI future, where they're announcing 2 major GPU clusters and sharing the different details related to the hardware, the network, the storage, design, performance, and all of the important information that allows them to extract high throughput and reliability from various AI workloads. So this is going to be the cluster design that they're going to be using for their Llama 3 training. And if I remember correctly, I believe there were rumors suggesting that Llama 3 would be released in July. Don't quote me on that. But this is definitely what we want to keep in mind as being the infrastructural backbone that allows a model like Llama 3 and its respective parameter variants to be possible in the first place. So Meta also wanted to make a point as well to show that they are strongly committed to open compute and open source, and how they've built these different clusters on top of a variety of different parts, including their Grand Teton, which we're going to be covering later, in addition to the Open Rack and touching a bit on PyTorch to continue and push their open innovation across the industry. And in addition to that, this is ultimately just one part of their roadmap, infrastructurally speaking, with the goal being by the end of 24, they want to continue to grow out their infrastructure build that will include 350,000 H100 GPUs, in addition to nearly 6,000 compute power equivalent, 600,000 H100s. So that last term, specifically compute power equivalent to nearly 600,000 H100s, doesn't necessarily mean 600,000 H100s. We're going to get to that in just a bit as well. But I just wanted to make that point early on that compute power equivalent will not necessarily all entirely be on 600,000 H100s. So again, overall, their data center sales cluster is going to consist of about 24,000 GPUs. And to give you all a quick idea as to what a cluster is in this context, if anybody isn't familiar, it's essentially a supercomputer with a bunch of different racks kind of stacked together. And we're going to get into what all of that means in just a moment. But just think in your mind a supercomputer that manages a lot of compute. So this sort of stereotypical data center image of there just being a bunch of like large stacked up computer shelves, if you will, of servers. And that's going to be what we're going to be focusing on as we continue delving into this. So Meta's long-term vision is to build AGI. Like that's what they're building this infrastructure for. And they want to build it in a responsible way that is widely available for everyone to benefit from. So in their efforts to work towards AGI, they're really working on scaling out their clusters to power that. And the progress they're making towards AGI is going to be focused on making available and creating new products with related to new AI features and a family of apps. So for context, some of these new features and application experiences include AI stickers, which you might have noticed as it relates to their AI image generation tool, Emu, and while also leveraging Llama 2 for that image generation model. So you get these little cute stickers that can be generated. You also get image editing with AI as a part of Meta's suites of tools that would be available from their Segment Anything model. In addition to various different assistants, or an assistant, I should say, that would be available within WhatsApp, Messenger, and Instagram, in addition to coming soon to their Ray-Ban smart glasses, their Meta smart glasses, as well as the Quest 3, through a custom model, again, leveraging Llama 2 as their latest large language model. And these different characters, in addition to that, with these different backstories, you might have seen some of them come up for these different famous individuals, and these characters being available through their different profiles on Instagram and Facebook. Now, a lot of this infrastructure will be set up in a way that will likely allow Meta to leverage their Llama 3 models once those are finished training. But for now, this is a lot of the different features and applications and items that are going to be relevant as it relates to what is being powered by this different parts of the infrastructure. Okay, just wanted to give everybody some context on that. Now, going back to the actual clusters themselves, Meta does actually have quite a bit of history in regards to creating clusters and using them, particularly for AI research, including 16,000 NVIDIA A100 GPUs that they had set up back in 2022. And for context as to what these types of superclusters look like, back as of 2022, they had also released a blog post. Let me just show you back in January here, where they essentially outlined visually what these different parts of their supercluster looked like. So as you can see here, we have three primary components that were broken down within the blog post as well. We have storage, we have compute, and we have networking. So all of these different boxes that are represented here each represent these individual core components of their superclusters found within data centers. So again, you kind of got this sort of warehouse setup where these different elements of the supercluster is stored. And again, you can kind of think of all of this as just a supercomputer for the sake of simplicity. So with that being said, they are ultimately working towards accelerating their open and responsible AI research by building their first generation of advanced AI models. If we go back, we can see Llama and Llama 2 were built with a lot of this infrastructure, and we're going to go into more context as it relates to that. But we're going to actually start with looking under the hood. Now, again, the blog post is broken up into network, compute, and storage. We're going to first start by focusing on networking here. So when it comes to their end-to-end experience, their cluster and what binds that cluster's compute and storage resources together are their network fabric, particularly as it relates to the two clusters that Meta is building. They're actually using two separate types of network fabric that relate to high performance compute, or HPCs. So in particular, they're using classic Ethernet. So if you think about Ethernet, you might be thinking about the Ethernet cables that you have that connect either to your modem or potentially to your router that allow you to essentially get online. These are similar types of Ethernet cables, just very much scaled up and customized and configured in a way that allows for high performance compute use cases, particularly as it relates to training and running generative AI models. And moving forward, when it relates to running AI models, I will be referring to that as inference, just using the more technical term that just means running a model. Okay, so if I say inference, just assume running models. All right. So with that being said, we're taking these two different networking approaches and doing our best to try and see which one is going to be the most worthwhile for future reference. That's part of the reason why Meta chose to use the different network fabrics and their respective infrastructure related to networking, because both of them each have their different pros and cons to essentially achieve RDMA, so remote direct access memory. So in the case of InfiniBand, we have our more new sort of network fabric designed to work with high performance compute in really scaling up and managing the compute resources that go into training and running inference with models. So for RDMA, which is really what one of the core things that you get out of InfiniBand's network fabric solution, you can think about that as random direct or remote direct access memory, or remote direct memory access, which is a way in which you essentially take storage, or you take memory from your storage devices, and you essentially, for lack of a better description that would get too complicated, you're basically teleporting them to your GPU resources. So normally you'd have to go through a much more roundabout process to go through your network in order to go from the CPU to the GPUs and all of that. And then in this case, you kind of get to skip that sort of step and just go right from the memory of storage to memory of GPU without running into issues of packet loss or latency. Now, for everybody wondering, packet loss is when you're running data through a network, and if there is any type of latency or essentially delay in the process of getting the data to its direct location, certain parts of that data can be lost, which is really bad for training models. You want to have as little latency as possible to prevent as much data loss that can occur. I remember reading that about nearly a third of the network was essentially being lost to latency. So their compute was essentially being wasted. The time and money going to that was being wasted. So in an effort to address that, you see this sort of application of InfiniBand network fabric, the InfiniBand network fabric, in addition to the different ways of addressing latency through the clusters, such as through this technique of remote direct access memory. Now, the way in which the data flows through the network is related to the Arista 7800 here. So, not there. So it's essentially what's known as a switch router. Now, the difference between a switch router, or what a switch router ultimately is, I should say, is a device that combines routers and switches to route data between networks within a data center. Now, the difference between a switch and a router is that a switch router is a, or I should say a switch is a device that connects multiple, or is a, I'm trying to think of a good way to phrase it. So a switch connects multiple devices to create a network, where a router connects multiple switches. So if you have a switch, you've connected multiple devices, and that in and of itself creates a network. And a router will then connect multiple switches to form a larger network. And you kind of have both all in one with the Arista 7800 right here. So in addition to that, we have two parts of our switch, which consist of this Wedge 400 and this Mini Pack 2. So if we take a look at this blog post that came out of Meta as well, they outline their Wedge 400 as a Tor for a more powerful open network. So a Tor is what's known as a top of rack or Tor switch, which is a type of switch or a box switch that connects servers and other devices within the same rack. So if we go back for a moment, let's actually dig more into what a rack is. So Meta has, for context, I feel like I should probably take another couple steps back here. So Meta is running the Open Compute project, which is an organization that was mentioned. Let me find it here. Open compute. Yep. So you're going to see the acronym OPC a lot in this article, or at least, hold on. See? No, really? No? Oh, CP. That's why. There we go. My apologies. You're going to see the acronym OCP a lot as it relates to the network, and a bunch of different parts within this this given set of cluster, or this given cluster uh, infrastructure. So OCP is an acronym for the Open Compute Project, which is an organization that shares designs for data center products and best practices among different companies, with Meta being one of the founding members of that organization. And this was really to kind of streamline and create consistency between data center designs and products, because if you have so many data centers owned by so many different companies, if you don't have a certain amount of consistency with that, then you run into a lot of waste and incompatibility that's ultimately more problematic for developing infrastructure in the long term, as opposed to having a more streamlined and open set of infrastructure available to work with in developing data center related products or data center designs. Now, when referring to the open rack associated with this network setup, we want to think about a server rack. So an open rack is specifically a type of server rack developed by any supplier certified as OCP compliant, and it provides a sort of consistent interface for the IT gear that it ends up supporting. Now, Meta has their own specification relevant to their hardware configuration. In fact, we can take a look right here. This is essentially what that rack looks like. And I'm sure you're all looking at that and thinking, yeah, that's a nice rack. Okay, so jokes aside, what a server rack essentially does is that it contains the different servers or nodes within it that allows us to build out to a larger cluster. So it's just a form of containment in a sense, and wiring up of different servers that allows them to be scaled up and distributed within a given cluster. So now, with that all being explained, now we have a good understanding as to what the rack is here, right? And we were just covering that wedge 400C and Minipack 2 as it relates to this design within this rack, right? And we again already covered RDMA. It's just a means by which we move data through different parts of the rack, so different servers and different parts of the cluster itself, right? So with that being said, let's go back here. So the other cluster features, InfiniBand fabric. Now, another quick bit of context, Ethernet and InfiniBand are really two completely different sets of network engineering. They're almost essentially at war with one another at this point, in that in terms of trying to get high performance compute, there are two approaches that are essentially mutually unintelligible or mutually exclusive from one another. They don't really have a lot of shared elements. They even have completely different protocols. So there isn't really a lot of transfer of information between Ethernet and InfiniBand. InfiniBand is also a lot more expensive and quite a bit newer. So these are different things that Meta is likely keeping in mind as it relates to the interconnection of their different racks as it relates to large-scale training for their models, which is why they are likely using both to get a fairly good understanding as to whether or not they want to apply both in the future, or if one ends up winning out as it relates to scaling. Now, ultimately, both of these solutions are providing an interconnected 400 gigabits per second for their endpoints. And to give you all some context, the average person in the US in terms of internet speed has about 219 megabits per second for download and about 24 megabits for upload. Now, The average developer might have something closer to like 500 megabits per second if they're really interested in getting good download and upload speeds, as well as 50% or 50 megabits per second for upload. And to give you all some more context, a gigabit itself could essentially be enough to stream 40K 4K videos simultaneously, 40 4K videos simultaneously, and be enough to back up an entire residential computer in the cloud basically overnight. So that's just 1 gigabit that you would get from that process. Now imagine 400 of those to get a better context of really how much bandwidth is available within these clusters. And we're easily seeing a situation where, at least in the case with Ethernet, we could potentially be going up to 800 gigabits per second. So now take that 400 and double it, and now you have 800 gigabits per second that could potentially be available within a given cluster, right? So that's more of the network process to go in mind. But I've kind of been dancing around the Wedge 400 and Minipack 2. So let's just go back to them really quickly. So in the case of those two, the Wedge 400 is a top of the rack switch that, again, just going over that too, it essentially allows for network communication between servers within a given rack. That's what a top of the rack switch is. It can usually be placed on the top of a server rack, with the rack we had seen earlier. It can also be placed in different parts, but it usually goes on the top. It looks like Meta had put theirs somewhere in the middle, probably for connecting between different tentons, if I have to guess. And in addition to that, we also have network switches. So in this case, the network switch that's being used by Meta is the Minipack 2, which is essentially Meta's own network switch developed in partnership with Broadcom. And a network switch is essentially a type of switch that connects different racks to one another. So the big difference between the two is that the Wedge 400 is initiating communication, network communication between the different servers within a given rack. So the Wedge 400 would be having general communication between the different tentons, which we're going to go into in just a bit. And then the Minipack 2 would be creating network connection, or would be connecting racks together in terms of their different network connections, right? So that's the difference between these different switches that we have available within our given rack. Then we have multiple racks, again, that make up that given cluster. So all in all, that's one of the main core elements of a given rack within an individual cluster, at least as it relates to networking. So with that being said, I'm going to pause real quick. I know I heard a few people wanting to ask questions. I'm just going to take a look at that for a moment. They're talking about that needs a supercluster. Okay, so that's a great question, Susu. So the size of a model is going to keep scaling up. It could potentially still be in the billions of parameters, but I wouldn't be surprised that if we see multiple models that are well above hundreds of millions of parameters, or just multiple models that are within the billions of parameters. So a lot of this compute at any one given time is not going to necessarily be used all at once for simply model training or inference. This is probably just going to be a fraction of the available compute to be used for different projects, such as maybe training a model and creating different checkpoints for that model, or potentially running a set of models for different applications for people using Meta's different applications, such as Instagram, Facebook, WhatsApp, what have you. So that's the first point. And held on a single RAM. You need more to be batch size times rate to be batch size times. I'm not actually sure about your second question, by the way. I don't believe one batch has to be held on a single bit of RAM. I believe the RAM is mostly just kind of the process by which that data is being moved to the GPU to actually do the batches. But I'm not quite familiar with the sequence length for all the different activations and how that would kind of all connect up in the context of the infrastructure here. Right. Yeah. I do want to clarify as well for everybody. I'm a software developer. I'm not really a hardware engineer or network engineer. I just kind of know things as it relates to these different topics and generative AI as well as AI more broadly. And I'm not necessarily going to have every answer as it relates to the very specific details. We're mostly kind of focusing on high level for the discussion here. So you have a better understanding of how the infrastructure generally comes together, at least on a rough conceptual level. So with that being said, we should probably also go over to the compute here. Now, for the compute, we have both clusters that are built on the Grand Teton, which is their in-house designed open GPU hardware platform. And that hardware platform, for the sake of simplicity and understanding, we can kind of think of it as a server. Now, it's not exactly a server. Technically, it's a CPU head on top of a set of 8 GPUs, usually in this context, H100s, which is what we'll often find within these different clusters, sets of H100s that make up a single Grand Teton. And this kind of goes back to Meta's original setup for infrastructure back when they were using CPUs. And we're not going to dig too deeply into this, but specifically, Meta initially had what's known as a Xeon hardware platform, which was leveraging primarily CPUs. But at a certain point, as it relates to AI models, once we got into the generative AI models that were where single models had billions upon billions of parameters, we couldn't really leverage CPUs as much, just given the load necessary to actually train these models and to run them and scale all of that for Meta's platform or Meta's different applications. This was good at the time particularly for more classical machine learning models such as LSTMs, convolutional neural nets, and I believe they had one other one I wanted to mention here. Sparse neural networks as well. Yeah. But as time went on and as these models began to get larger and larger, they had to move over to something that allowed them to do the necessary calculations, at least for model training, which is where we start to see their Xeon EX platform, which is really the next iteration on their Xeon hardware platform, which essentially added GPUs. For the sake of simplicity, that's really one of the big things that kind of came out of it. We still, again, see that RDMA over converged Ethernet, which is essentially RDMA for our Ethernet network fabric. But it was one of those situations where it really needed to scale up more for those relatively simple linear transformation calculations that we see with doing with linear algebra needed in order to actually train models, which is why GPUs ended up becoming a major component of this hardware platform. And from the Xeon EX platform, we then move on to the open hardware structure that we see in the announcement for the Grand Teton. So Grand Teton, and I'm not sure if I'm pronouncing this correctly, but essentially it takes that Xeon EX hardware platform and essentially consolidates it and optimizes it in a way that allows it to be more efficient with higher network bandwidth, higher power envelope, and essentially quadrupling the amount of GPU bandwidth. So in addition to that, they also consolidated it into a single chassis, which allowed for a higher rack power density in addition to just a more flexible means by which you could have all of the different components of the hardware platform kind of put together in a way that saved on space, saved on power from actually moving the different amounts of data within the actual hardware platform. And it was generally just a better optimization as it related to the open rack specification. So in addition to that, we go back over to the compute. we want to keep in mind that the Open Rack, the version 3 that we had seen earlier, would be where these hardware platforms, these tetons, would be stored in a way that would be a lot more scalable for building new clusters, which could easily be plug and placed in. And Meta has a history of developing GPU hardware platforms that goes all the way back to 2015. So this is more so they're kind of building upon this previous set of hardware platform for compute purposes that would be more specific to the needs of scaling up generative AI infrastructure as they build out and scale out larger and more robust generative AI models, such as their large language models, Llama 2 and the upcoming Llama 3. All right, so that being said, let's move on to storage. And storage is one of those types of parts of a cluster that really doesn't really get enough respect. We have training jobs that require a significant amount of data. And where there's data, you need to be able to store that data and retrieve it in ways that are more efficient and allow for flexibility of expanding upon that storage for more data to be made available for these clusters. So specifically, Meta uses for their storage platform a Yosemite version 3 Sierra Point platform, with their servers being based on that. And that platform is essentially, let's see here, it's a standardized and efficient, sort of flexible expansion or design for enabling high density flash storage on a given server. So essentially, it allows Meta to sort of build on their server platform in an open manner that can be effectively leveraged by the open compute community. So they have this 36-page PDF as it relates to explaining this expansion design specification. I didn't want to dig too deeply into that. I just wanted to give sort of a rough outline on it. But for anybody who's interested as well, they do link that in the blog post as well. And it's a good reference if you want to dig more into storage outside of that explanation. So in addition to that Yosemite expansion board design specification, we also have a need for storing checkpoints for given AI models. So when AI models are trained, there are checkpoints. You can kind of think of them like different versions of the model at different points of the training process, where we essentially end up storing these whole different versions of the models. And this tree structure, for the checkpoint tree structure, can be a bit messy at a certain point, depending on how it's managed. Like it can get to be a bit large and can require quite a bit of storage just to manage these checkpoints. And for that, we have this particular homegrown Linux style file system in user space, which is essentially a server specification implementation for a daemon or a program that runs in the background performing tasks, which, a daemon, for anybody who doesn't know, is a program that runs in the background performing tasks without direct interaction from the user. For the mount, mount is an operating system specific service to get a network file system off the ground. So things like validating user identity, checking access permissions, stuff along those lines, and a network file system protocol. So ultimately, that whole process is there to essentially provide a storage space for the different applications needed to train these models and to potentially run them on the user application side. So additionally have Meta's Tectonic distributed storage solution, for their flash media, which allows their different GPUs to save and load checkpoints in a synchronized fashion. And these different file systems, if we look at their tectonic file systems, it's essentially an exascale, so an exabyte scale distributed file system, or that includes what are known as multi-tenant file systems. And a multi-tenant file system is essentially just like a shared hosting file system where file systems are shared among either multiple users or multiple organizations. I would assume in Meta's case, it's probably shared between different users or different parts of their data center infrastructure. So with these different shared file systems, people can essentially, or I should say, different parts of their cluster can access data. And there's a gentleman with this video that kind of goes into more of the specifics, that explains the tectonic file system for scaling up to exabyte distributed file systems. So if you're interested in that, definitely check it out. And that's another important part of their storage process. So they additionally partnered with Hammerspace. And for anyone who is curious, Hammerspace is a data orchestration, or as a organization that looks like manages data orchestration across different data centers with scaling out software solutions for the automation of unstructured data orchestration and global file access across storage from different vendors for edge computing and data centers and on the cloud, or I should say at the edge and data centers in the cloud. So it's essentially just a software service provider that helps with managing unstructured data orchestration, or the management of unstructured data through a given data center in this case, or in a storage, in this case. So let's see here. Storage deployments. Yeah. So again, as we mentioned, the storage deployments for their different clusters for both Tectonic and Hammerspace are based on that Yosemite version 3 Sierra Point server platform. And they are upgraded with the latest high capacity SSD hard drives that can be found in the market today for their data centers. In addition to that high SSD capacity, the servers per rack were set up for the right amount of throughput capacity per server and rack count reduction. So the different Open Compute project servers end up acting as sort of Lego-like building blocks in a way that allows for a lot more fault tolerance. So say, for example, you need to change out certain parts of the storage, you can just plug it, you can just pop it out essentially and place in new essentially blocks for that storage in a way that doesn't disrupt any potential model training or any model inference that would be needed for other applications. So before we get to performance, I did see a question. I'm going to pop back over to that real quickly. Okay, so real quick, core differences between Ethernet and InfiniBand is that they're completely different network fabrics. Specifically, they both do RDMA slightly differently, and they're both different approaches to doing high performance compute. So in the case of InfiniBand, it's a bit newer, and it's a more, from what I understand, more straightforward process of doing random direct memory access. So in the case of Ethernet, you can technically do RDMA as well for the remote direct memory access, but there's a bit more of, it's a different approach for doing that. And it's something you kind of have to customize and set up. So InfiniBand is more expensive because essentially you have to gut all of your traditional network fabric and rebuild it from the ground up. And that's what's really makes it significantly more expensive. and for RDMA, what kind of software stack is used. I don't know offhand what software stack is used, but I know that it is essentially entirely different from the stack used for Ethernet, in the sense that like it has different protocols, it has different approaches to enabling RDMA, stuff like that. Again, I'm not a network engineer, so I can't really give anything significant beyond that. I hope that answers your question. Yep. All right. So now let's go to performance. So one of the big things they also focused on with getting this infrastructure set up was to maximize the performance and use of their respective racks and clusters without compromising performance or ease of use for the other. So one of the goals of creating good AI models is keeping the performance and the ease of use relatively simple and manageable, while still being able to scale out, um, in the case for performance, and being able to easily go through the process of training and running inference for these models. Specifically, they essentially just built these out to see how they would work. And from after building out these systems, they optimized and tested these different models, because ultimately simulating only goes so far in this process. And they ended up doing a comparison for performance between their small clusters with their larger ones to see where different bottlenecks are. So specifically in the case of communication performance between small and large clusters, you see a lot more inconsistency initially with the out-of-the-box large clusters versus the smaller clusters, which have a communication performance of around 90+%. And they end up explaining that for their performance, they ended up having to tweak a few things to optimize the full system for their larger clusters. Specifically, in order to address these issues, they did what was known as, let's see here, addressing and modifying their network topology. Let's see here, their network topology awareness. Yeah, so initially, one of the things that they did, well, they did several changes for optimizing for this performance, for how their internal job scheduler ended up scaling jobs, specifically with their network topology awareness. And again, network topology is essentially the physical arrangement of devices and cables in a given network and how they connect to each other. And it ultimately also describes how the logical flow of information goes throughout a network. So by enabling these jobs with network topology awareness, it gave them a much better understanding in how they could go about minimizing traffics going to their upper layers of the network, which additionally allowed them to optimize performance. So there wasn't any unnecessary issues with traffic that were coming as a result of ignorance of the arrangement of the devices themselves or how information flowed within them. So in addition to that, the collective communications library, they optimize their network routing with a NVIDIA collective communications library for essentially optimizing the network utilization, for getting greater expected performance to be on par with their small clusters and how they performed. So initially developing their larger clusters, they had to do a bit of tweaking essentially to get the communication going between get the communication optimized up to a certain threshold and above that certain threshold for their larger clusters. So they also worked on teams authoring and trading frameworks and models. Particularly, they used 8-bit floating point values. They used 8-bit floating point precision values for their training. And for context on H100s, really quickly, let's go over to here. In order to get a good understanding of how H100s look, I want to step back to not just the A100s, but to looking at consumer grade GPUs. So for a consumer grade graphics card, let's think about, say, a 4090 RTX, right? That's about 24 gigs of VRAM. Um, and relative to that, when you have an A100, the highest end A100, I believe, has 80 gigs of VRAM. So essentially, nearly 4 times the amount of VRAM as that commercial 4090 or that consumer grade 4090, right? So relative to that, uh, H100s particularly are just really beefy GPUs that, when compared to A100s, can train AI models such as, like, say, GPT-3 at least 4 times faster and up to nearly 10 times faster in some cases for other AI architectures relative to A100s. And when it comes to inference, they're nearly 32 times faster with essentially half the numbers of GPUs versus the A100s. And in terms of cost, I believe the last time I checked, an A100 is around $16,000 as of right now, with H100s being around, I believe it's $28,000 brand new. And with the recent release of the B2100s at the recent GTC, we have GPUs that can essentially get 2.5 to 3 times the performance when accounting for floating point differences. So I don't know if you all saw the GTC announcement, but there's this 1000x compute in 8 years kind of line chart, and it's a little misleading because of the different floating point precision values. Um, as you can see, our H100s, they're using a floating point 8 precision, which was mentioned in the Meta article. And for Blackwell, we essentially see a floating point 4-bit precision, which is essentially halved, which should allow for a lot more scaling of the number of calculations that can be done, essentially freeing up significantly more memory for doing those calculations at that 4-bit precision, but might potentially have some consequences as it relates to inference for these models. But again, remember, we're looking at the compute equivalent of about 600,000 H100s, not necessarily that there will be 600,000 H100s for Meta's generative AI infrastructure, which suggests that they're probably going to have some combination of leftover A100s from earlier, in addition to potentially purchasing the B200s that just came out. I know there was particularly this quote from Mark Zuckerberg himself about how AI already powers everything from our large language models to our content recommendation ads, essentially powering Meta and its different safety systems, which is going to only get more important in the future. And they're definitely going to be using NVIDIA's Blackwells to train their open source Llama models and build the next generation of Meta AI and consumer products. So again, it's probably not going to be an exact 600,000 H100s. It'll just likely be a variety of different graphics cards, GPUs that roughly equate to that amount of GPU performance. So let's see here. They also focused a bit on being able to debug their architecture. So like identifying a problematic GPU that could be stalling a training job. So having different software available for that debugability, and that sort of understanding of when an issue arises within the hardware is definitely something they focused on with their distributed collective flight recorder to expose different details of the distributed training, which makes it easier to identify an issue that could arise in a much faster and easier way. And in addition to that, they scaled up the AI framework that essentially powers all of these different AI workloads, or essentially made it more effective at scaling by essentially refining PyTorch to be a better AI framework for dealing with larger, more scaled up AI clusters or workloads as it relates to larger clusters for training AI models. And they end with this commitment to open innovation. And again, they've kind of highlight their open innovation and AI research within their community, and how they've been doing this for a while, how they're not new to an open approach to AI, and the importance of the future of Meta's infrastructure as they intend to hit their goals of having 350,000 NVIDIA H100s as a part of their total portfolio by the end of 2024. So that's ultimately kind of a high-level overview of all of this. So quick review. We've got the different racks with different clusters applying different network fabrics to essentially achieve RDMA, whether it's through InfiniBand or classic Ethernet. We have these Grand Tetons that essentially include 8 GPUs and a CPU head. The 8 GPUs will probably be H100s for the most part. And then we have the wedge for the server communication within a rack versus the intra-server communication within a rack versus the inter-communication from a mini pack. And then you have a bunch of 8 GPUs within another Grand Teton for your average rack here. In addition to that, you have the storage with these different servers that are based on the Yosemite version 3 platform, different SSDs, their own file system that's homegrown for their user space through a Fuse API, which is backed by their different partners for their Tectonic storage solution and co-developed by Hammerspace for their network file system. So with that all being said, we still have a bit of time for questions. Does anyone have any additional questions here? I'm gonna stop my sharing my screen here. I know it's a lot to go through in an hour, so if there's anything that you all kind of want to ask, I'll be happy to stay by for a little bit longer to answer questions.
Just wanted to ask if you can, like, there were many texts involved, and if you can, if you have a list of texts that links towards that and all the articles you shared during the call, if you have a list, that would be great to follow up with that and understand a few things there.
Yeah, absolutely. I can set up a list of the different links on like a maybe not a PDF, but yeah, like a doc of some kind. I could probably send that around. Definitely have that attached with the recording. All right. But yeah, any other questions? Like I said, I know this is a lot of stuff, and I probably could go into a lot more depth on certain things that I kind of had to gloss over for the sake of time. Certain things I can't quite do that for. Again, not hardware engineer or a network engineer. I'm just a software developer who dug into a lot of this stuff for the sake of understanding it or trying to understand it, because I know it's a lot of heavy jargon as it relates to tech infrastructure.
Hey, Mike.
Hey, Mike.
Oh, sorry, Steven, you can go ahead.
Sure. Mike, great talk. So the local llama community is really into just on-device generation and stuff like that. So there's a lot of enterprise heaviness in a lot of this training stuff. So what hopes are there for, or what do you see looking ahead for kind of like in your home, on your PC, that way of like literally training a generative AI model? Is that something that is just not realistic, or do you see that down the line some the local llama community and things like that could start to get into that?
So we're talking pre-training here, correct?
That's correct. Yeah, straight from the raw text and all that stuff. Yeah.
Okay. So there have been different attempts from the open source community to try and train up smaller large language models, or SLMs as they've been starting to be called. In terms of hope for that, there have been certain innovations as it relates to distributing pre-training. That seems to be the direction a lot of people are taking, sort of like a Tor equivalent of people agreeing to share resources and then bringing those together to create distributed pre-training. There hasn't been as much that I've heard about stuff along those lines recently. I have heard of a lot more innovations lately with different AI architectures that would allow for less of a requirement it would require less training data to train up comparably competent models, and that might be potential for a case for hope. Potentially quantizing could get to a point where we don't necessarily even need to train up models. We would just be able to rely upon taking models that have been released through open weights or through an organization like Meta or potentially Mistral, and then quantize them sufficiently to the point where they can be fit on an IoT device, for example, or potentially one's laptop or computer desktop, something along those lines. So there are different efforts being made from the open source community. I wouldn't fully count out anyone on that end, but I don't really see a path at the moment outside of those potential options for pre-training a larger LLM beyond like a max of like 10 billion parameters at this point. Like 7 is roughly where like around where we start to see people being able to scale up to a point 2, or are actually smaller in a lot of cases, like 3 billion or 1 billion. Is what you see out of a lot of research papers where they're testing things like different architectures, where they're pre-training a model from scratch. So at the moment, not quite, but we could potentially get there. I hope that answers your question.
Thanks a lot.
Hey, Mike, Kevin here.
Hey, Kevin.
Thanks for the chat, or thanks for walking us through how the infrastructure is built in the blog post. I was kind of curious, in summary, what are some of the main innovations here from like a hardware network perspective that made this, I guess, stand out and like, I guess, worthy of attention? I'm not really familiar with the history of these things. I recognize like the jump from A100 to H100, but in terms of just like the actual cluster building, like what is new and what, yeah, thanks.
So that's an excellent question, Kevin. I think a lot of it ultimately boils down to the sheer scaling. I think that's really one of the big draws for why this is kind of a big deal. Like one of the things I didn't actually get to show for today's the review of the blog post was this Llama 2 paper. Now, for context, I believe Llama 1 was trained on one cluster with about 2,000 NVIDIA A100s. And I believe in the case of Llama 2 here, if we actually look at the training details, we can scroll down a bit. They do mention the use of more than one cluster. I believe there's a section here. Oh, not that. All right, let me go back up for a second. Come on. Oop. Let's see here. Training details, parameters, missions. Yeah, so up to 2,000 GPUs, pre-training even more, and models on research. Both clusters. So they say both clusters use NVIDIA H100s as it relates to the different clusters being used to train Llama 2, which suggests to me that they used at least 2 clusters of 2,000 A100 GPUs. Now, again, the new clusters that are being built by Meta have about 24,000 GPUs, right? So we're going from 2,000 GPUs per cluster that are A100s to potentially 24,000 GPUs that are these H100s that are a step above. So I think that's really what a lot of people found just really like noteworthy about this announcement. It was just the sheer scale of how this technology is being built out and invested into. Because for context, an H100 is about, I believe, around 25, 30K nowadays. So 25, 30K for a single Grand Teton, you're looking at about $250,000 to $300,000 for just a single Grand Teton. And I believe these racks contain, based on at least the image that we saw here, at least 2 Grand Tetons per rack. So you're looking at nearly $1 million worth of hardware for just one rack. And when we see how that kind of compares to these previous superclusters, each one of these like orange boxes that we saw earlier, are essentially, actually, let me share my screen here. Each one of these, geez, hold on. Here we go. And boop, badoop. All right. So there we go. So each one of these orange boxes here are essentially a singular rack. So just again, just the sheer scale more than anything is what's really, I think, getting a lot of people's attention, because this is billions upon billions of dollars going into these clusters. We're talking, I believe, for the total cost when we account for all the GPUs, roughly around like the $300 billion mark, roughly around there, if I remember correctly. So I think that's really the big draw more than anything.
Yeah, and being able to pull all those resources together and still train something.
I'm sorry, Kevin, you're coming in a little quietly. What is that?
Oh, I'm sorry. Can you hear me now?
Yes, perfectly.
Okay, great. Yeah, I was just saying that to scale, like have like a 10x scale, but then also be able to manage performance and reliability and all that stuff to train the next generation model. Yeah, I guess that's the true innovation here. Got it. Yeah, makes sense. Thanks for referencing the scale. That helps me put it into perspective.
Yeah, that's something that I think is really one of the bigger takeaways, just being able to manage that scale without everything just essentially collapsing in on itself or not working at all or reaching certain structural bottlenecks is really, I think, one of the major elements of this that part of what makes this really just noteworthy and impressive from Meta's part, because they went from a relatively small set of AI infrastructure for largely research purposes to scaling out full production enterprise level infrastructure, their own data center setups, their own superclusters, use of these superclusters and clusters for research in addition to running AI for large scale applications, potentially being used by millions or billions of people at a time. So really, AI in Meta seems to have come quite a long way over the last few years, and will likely continue to do so as they move towards AGI.
Got it. Yes. Very impressive. Thank you.
Yeah, very welcome. Anybody else? Any other questions? All righty. Well, if there are no further questions, I'm going to end the recording here. Let's see here.